Hello, Matthews Gatos here. In this video, we're going to cover completing the square. But before we do that, let's do some review questions based on 3.2. So in this question here, we have Mateo riding his dirt bike off a ramp. Now the path that he follows off that ramp can be modeled by this quadratic function. H of d equals negative 3.9 d squared plus 13.1 plus 8.7, where d is the horizontal distance from the ramp and h is the height, both measured in meters. So I want to know how far away from the ramp to the nearest tenth of a meter does he land. So what I'm going to do, the first thing I'm going to do is put this into my graphing calculator and adjust my windows so that I can see the whole graph. So I did that, and you can see the window setting that I used, and this is what the parabola looks like. So if I want to know how far away from the ramp he landed, is that going to be point 1, 2, 3, or 4? So the trick to these questions is not only knowing what point to be able to solve, but then actually solving for it. So let's talk about each point. Okay, so point 1, well, point 1 makes no sense because in point 1, the horizontal distance would be negative, and you can't have a negative distance. Okay, point number 2 would actually be the y-intercept, the point at which he started the jump from. So that's not going to make sense. Point 3 is the maximum height that he reaches from on the jump, so that one isn't right. So it has to be point number 4. So point number 4 tells me how far away from the ramp he is when he lands. So he's on the ramp, he jumps up, reaches a maximum, comes back down. Point 4 is the point that I'm looking for. So putting that into my calculator, my graphing calculator, you can see where it intersects the x-axis, where the height is 0. Again, remember here, 0 in disguise. So when the height is 0, because he landed, the time will be, the distance will be 3.9 meters from the start of the ramp. Okay, let's look at this one here. So we have in this question here a projectile, and it's given by this equation. H is the height of the projectile above the ground. D again is the horizontal distance from the launch pad, both again measured in meters. So I want to know how far away from the launch pad is the projectile when it begins to fall to the nearest tenth of a meter. So again, what I did is I put it into my calculator, and you can see I adjusted my window there, and I have my 4 important points. So I want to know which one of those 4 points will answer, or will be the answer to my question. So let's go through all the points together one by one. So again, point 1, you can see that my x value is negative, which is a distance, and you can't have a negative distance, so that doesn't make sense. Point 2 is my y-intercept, where the projectile starts. So before I shoot it, that's the height of the projectile, so that won't make sense. Point 3 is the maximum, the vertex. Now remember about the vertex, it's the point at which I change directions. So I'm going up, 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 and when I reach this point, I start to turn around and I begin to go down, down, and down. That's the point that I'm looking for. How far away it is from the launch pad when it begins to fall. So at point 3 is when it starts or changes direction, it starts to fall. So that's what I'm going to be looking for. So I can put that into my calculator, excuse me, and I can find out what my maximum point is. So we have to decide whether I need the x coordinate or the y coordinate. So it comes back to looking at how my variables were defined. So in my question here, h, which really corresponds to y, is the height of the projectile above the ground. D, which is my x value, is the horizontal distance from the launch pad. So I want to know how far away it is from the launch pad, which is my x coordinate. So this here would be my maximum height, but that's not what they're asking me for. They're asking for the distance from the platform. So here I can see rounded to the nearest tenth, it's going to be 7.7 meters. Okay, so in this video here, 3.3, I'm doing it in two parts. I'm going to look at completing the square, what exactly that is. In this video, I'm going to look at how to complete the square when a equals 1. So when this number in front of x squared is 1. In part 2 of this video, I'll look at what happens when it's not equal to 1. So before we begin talking about completing the square part of that process is actually turning your quadratic into, at least in part, into a perfect square trinomial. So in 10C, we dealt with perfect square trinomials, and I just want to back up the bus and talk about that and make sure you understand why it's actually called a perfect square trinomial. So a perfect square trinomial is any kind of a trinomial that can be written as the product of two identical binomials. So here's a nice example. X squared plus 6x plus 9 equals to x plus 3 squared. So looking at this, I like to look at things from a geometric perspective. Everything in math has a root in geometry. So let's look at how this fits together. So remember back in junior high when you used your algebra tiles? Don't worry, I'm not going to get you to use them now. I just use these as an illustration. So we had our x squared tile here, and we had our x tiles, and notice that there are 6 of them. 1, 2, 3, 4, 5, 6 variable tiles. And then the little guys are my ones tiles, and you can see I have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. Now I can fit those together so they form a square, an actual geometric square. The dimensions of that square are x plus 3 by x plus 3. So you can see the length along here is x and then 3 little ones. The length along here is x and then 3 little ones. So it equals to x plus 3 squared. So it's called a perfect square trinomial because it actually forms a square. And the polynomial x squared plus 6x plus 9 is the area in the middle. When I factor it, the factors are the length and the width. So since they're the same, it's a perfect square trinomial. So I want to take this idea here of taking a perfect square trinomial and move away from the tiles. So starting with the tiles, just so we can move away, notice that x squared is a perfect square because it has two identical factors. It has a factor of x by x. So x squared is a perfect square. Notice that 9 is also a perfect square because look, 3 times 3 equals 9. So 9 is also a perfect square. Now my middle term 6 is not a perfect square, but if I divide 6 into 2 equal pieces, I get 3x and 3x. So that's the requirements for a perfect square. The first term is a perfect square, the last term is a perfect square, and this middle term, if I divide it by 2, which is 3x plus 3x, I get the square root of the first term and the square root of the last term. That's the requirements for a perfect square trinomial. So let's look at this without the tiles. So without the tiles, I start with my perfect squares. So the first and the last terms are perfect squares. And then what I'm going to do is take my middle term, which is 6x, and I'm going to divide it into 2 equal pieces. So 6x divided by 2 is 3x and 3x. And then to factor, all I have to do is take the greatest common factor of each row or column. So factor out the GCF from each row or column. So x squared and 3x. Do you see there they have a common factor of x? 3x and 9 have a GCF of 3. Same thing this way here. X squared and 3x is 3 GCF, sorry, of x, and 3x and 9 has a GCF of 3. Okay, now because this 3x is positive, I can take the positive out. Because this 3x is positive, I take the positive out, and that's how I factor. So this idea of creating perfect squares and factoring, we're going to put that all together and see how we do that with questions that don't start as a perfect square trinomial. Let's not get too ahead of ourselves. So let's try this one here, factoring x squared minus 10x plus 25. So I'm going to look at the first term, which is a perfect square, and the last term, which is a perfect square. Now I notice that this negative 10x can be split into 2 equal pieces. negative 5x, and negative 5x. So I'm going to write those there. So I'm going to factor out the greatest common factor from each row and column. And a little tip I have for you is if the leading coefficient is negative, always factor out a negative GCF from that row or column. Okay, so let's go with our rows here going across. So I have an x squared and a negative 5x. They both have an x in common, so I'll take that out. Let's look here, negative 5x and 25. So first of all, I notice that they have a common factor of a 5, but since the leading coefficient is negative, I'm going to take that negative out and factor out an x minus 5, so a negative 5. Let's look at my columns now. So x squared and negative 5x have a common factor of x. My leading coefficient is positive, so I'm good. Negative 5x and 25 have a greatest common factor of 5, but because my leading coefficient is negative, I'll take out a negative 5. So I know that this factors as x minus 5 times x minus 5. Now, if factoring isn't your strongest area, this method here is a very nice graphic organizer. And it's nice because you can always check. X times x is x squared. Negative 5 times x is negative 5x. X times negative 5 is negative 5x. Negative 5 times negative 5 is 25, so I know I did that correctly. Okay, let's try a question here with a little bit of a twist. So I have x squared plus 20x plus what would make it into a perfect square trinomial? So let's use x squared here. Now I know because it's a perfect square trinomial, I'm going to take 20x and divide it into 2 equal pieces. And I want to figure out what number goes here to make it a perfect square. So let's go ahead and factor out a greatest common factor. So in this first row here between x squared and 10x, I know I have a GCF of x. In here, x squared and 10x, I have a GCF of x. So I know I'm on the right track because x times x is x squared. So if I want to have 10x, x times what number up here would give me 10x? Well, x times 10 would give me 10x. And the leading coefficient here is positive, so I'll take out a positive. Same thing for this down here. If I have 10x, x times what number will give me 10x? Well, we know that's a 10. And because this is a leading coefficient that's positive, I'll take out the positive. So you can always check. X times x is x squared. 10 times x is 10x. X times 10 is 10x. So I know that's perfect. So what is missing here is 10 times 10, which is 100. So if my quadratic was x squared plus 20x plus 100, I see that that is a perfect square trinomial, and it factors as x plus 10 times x plus 10, or x plus 10 squared. Okay, in this question here, we're going to complete the square. So here's how I know it's not a perfect square trinomial. This last term is not a perfect square. Not a perfect square. So what I'm going to do is I'm going to borrow what I did on that last question, and I'm going to say if I had y equals x squared plus 14x plus what number would give me a perfect square trinomial? So let me just pull that off on the side because I want to make it into a perfect square. So since I'm making it into a perfect square, that's a perfect square, goes there. I'm going to take 14x and divide it into 2 equal pieces, which are 7x and 7x. So using my pattern, greatest common factor along here is x, greatest common factor along here is x. X times x is x squared. So I asked myself, x times what number would give me 7x? That would be a 7. So since this is a positive leading coefficient, I take out my positive. So x times 7x, yes, 7x. Similarly here, x times 7 will give me 7x. So since my leading coefficient is positive, that's what comes out. So 7 times x, 7x. We're good. So I know that 7 times 7 is 49. So if this polynomial looked like this, y equals x squared plus 14x plus 49. If that's what it looked like originally, it would be a perfect square trinomial. But I can't just randomly add a number. I can't just add 49 because I've changed the value of the quadratic. So my tip here for you, if you add a number, subtract it as well to maintain balance. Here's what I mean. So if I add 49, I'm also going to subtract 49. Now that kind of seems bananas, right? Adding 49 and subtracting 49, that's just zero. I've just added zero to that expression. But that's actually a good thing, because if I can add zero to any expression without changing it. Now remember when we started, it was x squared plus 14x plus 8. So I really have x squared plus 14x because this whole thing is 0. So I'm just going to go back up here and add on the 8. So at this point here, I haven't changed the question. It looks different, but I haven't really changed it because that 49 take away 49, this whole thing here is actually 0. So x squared plus 14x plus 0 plus 8 is still what I started with. So what I'm really going to do here is I want to focus on my perfect square trinomial. So let me just highlight that for you. This right now is my perfect square trinomial, and that's what I'm going to focus on. So looking at my perfect square trinomial, I know from above that factors as x plus 7 times x plus 7, or x plus 7 squared. That's the whole purpose of why I do this, because I can see clearly how it factors. And then all I do is combine my like terms out here. Negative 49 plus 8 is negative 41. So what I've done is I've taken a question that was not a perfect square trinomial and I completed the square. So this part of the question is a perfect square trinomial, and this is what's left over. Now the benefit of doing this is my original equation, if we go back up there, in my original quadratic, I cannot tell looking at this question what the vertex is, but through the process of completing the square, I can now easily see that my vertex is negative 7 and negative 41. Now I want to show you that I actually did this correctly, and you can do this for every question that you do as well. If I want to know, are these two actually equal, I can go into my graphing calculator like this. So in y1, I put my original question, x squared plus 14x plus 8. And in y2, I put in my completed square form, which was x plus 7 all squared minus 41. And you can see, the check always happens in the table, you can see that they are in fact equal, which means I completed the square correctly. So this idea of completing the square, taking a trinomial or a quadratic and turning it into, at least in part, a perfect square trinomial, is the process that we do to go take a quadratic from standard form to vertex form. So let's try another one. I want to complete the square and state the vertex. So right now I know it's not a perfect square because 5 is not a perfect square. So let's focus on just this part here. So x squared, take negative 8x and divide it into 2 equal pieces. Now let's use our process of factoring. So greatest common factor along here is x. Greatest common factor along here is x. I know that here I'm going to have to take out a 4, but the leading coefficient is negative, so take out a negative 4. Same thing here. I'm going to take out a GCF of 4, but again, because this is negative, I also take out the leading coefficient negative. So let's check to see if we've done this right. X squared is x times x. Negative 4 times x is negative 4x. X times negative 4 is negative 4x. So I know I'm on the way to a good solution. So to complete the square, negative 4 times negative 4, I would need positive 16. So I'm going to rewrite my quadratic as follows. X squared equals, y equals x squared minus 8x plus 16. That now makes it a perfect square trinomial. But since I added 16, it changes the value, so I'm also going to subtract 16. So what I've added right now is 0. 16 take away 16 is 0. And then I add on my plus 5 from above. So I have not changed the question because the 16 minus 16 this piece in here is actually equal to 0. So I've really just added on nothing. So again, I'm going to highlight my perfect square trinomial, which is right here. And then I'm going to combine my like terms on the outside. So I've got y equals x squared minus 8x plus 16 factors as x minus 4 times x minus 4, or x minus 4 squared. And then I just combine my like terms on the outside. Negative 16 plus 5, negative 11. So now I've completed the square, and I can state my vertex, which is 4 and negative 11. So hopefully that process makes sense and you understand now why we're actually doing it. So now I share with you a tragic tale of perfect squares on their honeymoon. So this newly married 2 and 5 come together. They go through the tunnel of love, not realizing that it is a square root tunnel of love. And 2 and 5, or 25, go in, but only 5 comes out. What a tragedy. Shakespeare has nothing on this girl. Okay, so I hope this video helped. You can go on and do practice questions at the end of my notes, and then move on to your textbook questions. And I look forward to seeing you for part 2, where we look at what happens when a is not equal to 1.